Titan is one of the most remarkable worlds in our solar system. It is a moon of Saturn, but it is larger than the planet Mercury. What makes Titan truly special is its atmosphere. It is the only moon we know of with a thick atmosphere, even denser than Earth's. This sky is a thick orange haze, made mostly of nitrogen, with a little bit of methane. The result is a world that feels strangely Earth-like, yet profoundly alien. It has weather, winds, and seasons. On Titan, the clouds are made of methane, and it rains liquid methane instead of water. This is a world of incredible cold, where water is frozen as hard as rock. Rivers carve icy channels and flow into vast lakes and seas. To understand why the new discovery is so important, we have to think about a basic chemistry rule, often summarized as like dissolves like. Molecules with a similar electrical structure tend to mix well together. Water is a polar molecule, with a slight positive end and a slight negative end, like a tiny magnet. Polar solutes like salt and sugar dissolve easily in water. Nonpolar molecules, like oils and fats, lack that separation of charge. This is why oil and water do not mix. Water prefers other polar molecules. On Titan, we find both polar molecules and nonpolar molecules. The lakes of methane and ethane are nonpolar, simple hydrocarbons. The atmosphere also makes polar molecules. One of the most important is hydrogen cyanide, HCN. HCN is made of hydrogen, carbon, and nitrogen, and it is polar. On Earth, HCN is a key precursor to amino acids and nucleobases, so we expected nonpolar liquids to sit on the surface while polar HCN solids rained down, staying separate. New research has overturned this long-held assumption. Scientists at NASA's Jet Propulsion Laboratory tested what happens under Titan-like conditions, cooling a chamber to about 90 Kelvin, or minus 180 Celsius. They mixed polar HCN with nonpolar methane and ethane. Using spectroscopy, they shone light through the samples and read how the solids formed. Instead of segregating into separate crystals, something unexpected appeared. Polar HCN and nonpolar hydrocarbons came together into a single, unified solid, a co-crystal. HCN formed a rigid, repeating lattice with tiny pockets inside. Methane and ethane fitted into those pockets, locking into a stable, ordered pattern. Chalmers University ran powerful simulations to test thousands of arrangements. They identified the most stable structure that matched JPL's spectroscopic signals. The result independently confirmed a co-crystal, hydrocarbons inside a polar HCN lattice. At Titan's extreme cold, familiar chemistry rules can bend toward the lowest energy packing. This ordered packing becomes the most efficient, stable outcome. The HCN hydrocarbon co-crystals challenge the oil and water principle. On Earth, with plenty of thermal energy, polar molecules flock together and push non-polar ones away. Constant motion and hydrogen bonds make like dissolves like reliable. At 180 degrees Celsius, molecules move slowly and the system seeks the lowest energy solid. The drive for tight packing can overpower the usual polar-nonpolar repulsion. HCN builds the scaffold. Hydrocarbons act as fillers to minimize energy, like different blocks snapping together to make the most compact structure. Co-crystals are known in labs, but finding them naturally on a planetary scale is a shift in thinking. Earth-based intuition can fail in alien environments. Titan's organic sand might be composite. Polar and nonpolar molecules lock together. Our picture shifts from chemical segregation to intimate molecular mixing that could boost reactivity. This discovery dramatically expands the possibilities for prebiotic chemistry on Titan. Co-crystals can store polar HCN within a nonpolar matrix, bringing key ingredients together. Imagine them as tiny, self-contained chemical packages. They might form in the atmosphere and snow down or frost onto the ground. As seasons change, or after rare impacts, these crystals could transform. Slight warming may release hydrocarbons, leaving porous, reactive HCN ice. If dunes are co-crystals, their density, hardness, and wind transport could differ from old models. In lakes and rivers, co-crystals may dissolve and reprecipitate, concentrating or releasing HCN over time. This cycling can bring ingredients together to build more complex molecules, the next step toward life. It also links the organic rich surface with a deep liquid water ocean. Impacts or cryovolcanic water could mix with co-crystal deposits, creating brief warm chemical soups. Since HCN is common in space, similar co-crystals could enable prebiotic chemistry across the cosmos, even in deep freeze. This sets the stage for the next chapter of Titan exploration. NASA's Dragonfly, a nuclear-powered rotorcraft, will launch in the coming years and arrive in the 2030s. Unlike a lander or orbiter, it can hop across Titan to sample diverse terrains. With advanced instruments, it can test the co-crystal hypothesis directly in dune sands and crater floors. Confirming co-crystals on Titan would be a monumental result. It would also map how and where they're distributed. Curiosity led to lab experiments, confirmed by simulations. Now a robot will test them on another world. Observation, hypothesis, and verification drive science forward. This finding teaches humility. Rules from Earth aren't always universal. By pushing into extremes like Titan, we learn about alien worlds and the principles that govern the cosmos. Could life begin in a place so cold and strange? We don't know. But Titan's unexpected mixing makes the question more compelling than ever. Enjoyed this? Like and subscribe for daily science-based content.